Welcome back, dear students. In this session we shall discuss about the Fourier analysis of the square wave. Usually square waves are generated by using the addition of sinusoidal waves of different frequencies. If we add the odd harmonics, then we will get the square waves. We have a square wave represented in this figure. You can observe the amplitudes are represented as plus A and minus A along y-axis, and the square wave represented here is a function of time, where the time is plotted along x-axis. We have from the Fourier theorem, any periodic function is given by f of t is equal to a naught plus summation n is equal to 1 to infinity of a n sin n omega t plus summation n is equal to 1 to infinity bn cos n omega t. So this is the mathematical representation of Fourier theorem. Let this expression be 1. So in this expression we have a naught, a n and b n, which are called as the Fourier coefficients. Now any square wave can be mathematically represented as a function f of t which is equal to a for the time between 0 and t by 2, or it can be represented as the time between 0 and pi, and the function will be equal to minus a for time between t by 2 and t, or it can be represented as the time between pi and 2 pi. Here in the figure you can observe the function f of t is equal to a, that is, the amplitude is maximum for the time between 0 and t by 2. So in this 0 to t by 2 the amplitude is maximum. So therefore this function f of t having a maximum amplitude between the time 0 and t by 2. Similarly, the function f of t will have a maximum amplitude in the negative axis direction, that is minus a, for which the time between t by 2 to t. So from t by 2 to t, so it is, the function can be represented as it is equal to minus a. So therefore it repeats periodically, the function repeats periodically, hence a square wave can be represented as simply the amplitude a or minus a. Now let us evaluate the Fourier coefficients for the square wave. Let us consider the Fourier coefficient which we have derived in our earlier session, that the Fourier coefficient a naught is represented as a naught is equal to 1 by t into integration of f of t with respect to t from 0 to t. So here f of t can be integrated from 0 to t, or else we can integrate the function f of t between the limits 0 to t by 2 and between the limits t by 2 to t, and if we add this and we get a function of f of t integrated between the time limit 0 to t. So hence we can split this and we can integrate from 0 to t by 2 as well as t by 2 to t. So we can substitute for f of t a. The function f of t will be is equal to a when the time limits are 0 and t by 2. Similarly, the function f of t can be represented as minus a between the time limits t by 2 to t. Now, if we integrate this function, we will get a into t, and here also we get a into t. A is taken constant and it is taken outside, and we have to apply the limits 0 to t by 2 and t by 2 to t. By applying the limits, we get a by t into t by 2 minus 0 for the upper limit t by 2, and if we apply the lower limit it will be minus 0. In this second term, if we apply the upper limit and lower limit, we get minus t plus t by 2. On simplification, we will get a naught is equal to 0. Hence, in the Fourier analysis of a square wave, the coefficient a naught is equal to 0. Now we shall evaluate the Fourier coefficient an. For that, we can write the expression for the Fourier coefficient an as an is equal to 2 by t integration of f of t sin n omega t with respect to t between the limits 0 and t. So this is also we have derived, or we have found and we have discussed it in the previous session of the Fourier analysis. For this, let us have the integration, and we can split this time limit 0 to t as 0 to t by 2 and t by 2 to t, and integrate the function. And here also for f of t, we can put a for the time period 0 and t by 2, and we can put minus a in the time period t by 2 to t, and we will integrate this term. We will arrive at 2a by t into integration of sin n omega t will be minus cos n omega t by n omega, and we apply the limits 0 and t by 2. For the second term, the integration of sin n omega t will be minus cos n omega t by n omega, and this minus into minus will become plus, and these are the two limits applied, t by 2 and t. And if we apply the limits t by 2, we will get for the first term it is minus cos n into, for the omega it will be 2 pi by t, and into t by 2. For this second term also we will apply the limits like this, and we will arrive in the next step that it is 2a by t n omega into minus 2 cos n pi plus 1 plus 1, because cos 0 is plus 1 we get. So next we will get 2a by tn into, you substitute for omega, that is 2 pi by t, into 2 minus 2 cos n pi. After simplification, we get the term an is equal to 2a by t into n into 2 pi by t into 1 minus cos n pi. So here we have to put the value for cos n pi. If n is an odd number, cos n pi will be minus 1, because we have for cos pi, cos 3 pi, cos 5 pi, etc., we will have the value of -1. And for n is an even number, for cos 2 pi, 4 pi, 6 pi, etc., the value will be 1. So therefore, we can write for an is equal to 4a by n pi. After putting the values for odd number of n value and even number of n value, we will get this. So for odd n, an is equal to 4a by n pi, and for even value of n, we will get an is equal to 0. And this can be written in general, an is equal to 2a by n pi into 1 minus of -1 to the power n. So here if you put the value from 1, 2, 3, etc., we will get the value for the Fourier coefficient an. So hence this is the expression for the Fourier coefficient an in case of a square wave. Now we will evaluate the Fourier coefficient Bn. So as we have from the previous derivation of Bn, the Fourier coefficient Bn is equal to 2 by t into integration of f of t cos n omega t with respect to t between the limits 0 and t. So here also we can split this integration between 0 to t by 2 and t by 2 to t and put the value of f of t as a and minus a, and we will integrate. After integration, we get 2a by t into the integration of cos n omega t will be sin n omega t by n omega, and we have put the limits 0 and t by 2. In the second term, it will be sin n omega t by n omega between the limits t by 2 to t. After applying the limits for t, the upper limit is applied, therefore it becomes sin n into, instead of omega, it will be written as 2 pi by t into applying t by 2 for t, it will be this one, and for lower limit 0, the sin 0. In the second term, applying the limits upper and lower limits, we get sin n into 2 pi by t into t minus sin n 2 pi by t into t by 2. After simplification, we will get that is equal to 2a by t n omega into sin n pi plus 0, because sin 0 is 0 in the first term, plus sin 2n pi minus sin n pi. So here also we have the values for sin n pi is equal to 0. By putting the value of the sin n pi, we get the value of the Fourier coefficient Bn is equal to 0 in case of square wave. Next, substituting the values of the coefficients such as a0, an and Bn in the Fourier series in the equation 1, that is the Fourier series equation, we will get as f of t is equal to 0, that is for a0, plus for an we will get summation n is equal to 1 to infinity 2a by n pi into 1 minus of -1 to the power n plus 0. Then the complete series will be f of t is equal to 2a by pi into sin omega t plus 1 by 3 sin 3 omega t plus 1 by 5 sin 5 omega t plus etc. 1 by n sin n omega t. So here you can observe these are the odd harmonics of the sine function. The addition of such successive terms of this series, we will get the Fourier series like this. The complex function will be like this. For sin omega t term, we will get a function like this. So it is shown in this figure 1. In the next figure, the series will be seen like this. It is for 1 by 3 sin 3 omega t term. For sin omega t plus 1 by 3 sin 3 omega t term. So if you add these two functions, the resultant series will be like this. You can observe the resultant series, the variation of the amplitudes. You can observe. Still further, if you add the term sin omega t with the 1 by 3 of sin 3 omega t and 1 by 5 of sin 5 omega t term. So if you add these three functions, we will get another type of series which is seen like this. So it is a little bit a form of a square, you can observe in the figure. Again, we can add any number of sine waves, and here is another function using 20 sine waves. We get sin x, so that is in terms of omega t, x in terms of omega t, plus sin 3x by 3, that is 1 by 3 sin 3x, or 1 by 3 sin 3 omega t, plus 1 by 5 sin 5x, etc. So like this, if you add 20 sine waves, so we get a waveform like this. You observe, so it is clearly a square in shape. Hence, the above figure shows that the addition of successive terms of the above series leads to the square wave pattern. It is seen from the figure that as more and more terms are taken into account, the displacement curve approaches nearer and nearer the square wave pattern. And if you add more and more number of the sine waves, we will get a smooth square wave function. So this is about the Fourier analysis of the square wave.